Hello everyone, in this video we will see about force and torque sensors in robotics. So first coming to the motivation, so why we are going for this torque and force sensors, that kinematic constraints. So it refers to the limitations imposed by the environment on the possible paths the end effector of a robot can follow. Next, position control. So position control, which focuses on precisely controlling the robot's position, is suitable when the robot is following a predetermined path in space. However, this may not be enough when the end effector comes into contact with the environment. Okay, so in other words, like speaking, what we can say is, while position control works well for planned movements, it may fall short when the robot needs to respond to contact with the surroundings. This is because additional control strategies like force control are often required to ensure the robot's actions are appropriate and safe when interacting with objects or obstacles in its environment. Okay. So next, we'll see what is force control. So it is essential for a robot to manage its physical interactions with the environment, especially when it needs to manipulate objects or work on surfaces. Force feedback and control are vital in such situations to ensure the robot can adapt, work effectively in less structured settings, and operate safely around people. This is particularly important for tasks like polishing, deburring, machining, or assembly, where precision and safety are crucial in this. So coming to force torque sensors. So the importance of force and torque sensors in robotics, commonly this is used in robotic applications, you know that. They give vital feedbacks to the system, alerting the controller when changes are present in the work process. Force control is often used in robots that work in the assembly process by relaying information about the operation status. Okay, so robotics using this force and torque technology can more closely replicate the motions and dexterity of human hands. So this allows them to work on more delicate processes that were previously only possible using human labor. Okay, so as this technology improves, robots can work in a broader range of assembly and manufacturing fields. Okay, without specific sensors, most manufacturing robots operate under predefined parameters for speed and path. To work in processes that require adaptive movement, a robot needs some external input to know how to vary its movements to fit the changing parameters within the system. Okay, some examples like part fit up, sanding and polishing, and also deburring, okay, as we have seen earlier. So with the addition of force and torque sensors, robots can feel the task they are working on, okay, making them more versatile in the manufacturing process. So you can see here the same example where what we have seen, the harmonic drive in a manipulator where the torque sensor is placed. So okay, with the digital interface. And here nearby that you have harmonic drive unit. So next, the force torque measurement. So we are going to see the relationship between the force and torque sensor. So first, two motor current sensor. So torque is proportional to the current. Okay. So the proportionality can be replaced by some constant. So I am representing here it as K, a subscript of T. Okay. So from this I know what is the current. So here current is measured as torque by the constant. Okay. Next, force and torque relationship. We know that torque is measured as force into distance. So from this, force can be forces, torque to the ratio of distance, and force. So torque we have already found as from the previous expression. We can take the torque as current into the constant. Okay, so that can be here replaced for the force sensor, so that this give the force and torque relationship. Okay, so force will be equal to current into constant by the distance. Okay, so this method is indirect and inappropriate. So we go for different types of force or torque sensors. So one by one are piezoelectric sensors, piezoresistive sensors. This is strain gauge based. This is mostly extensively used in the force control and robotics. So we will see the working of this in detail about this strain gauge based piezoresistive sensors. And the next one is capacitive force sensors. So these are types of force attack sensors. Okay. So force measurement using strain gauge. So you know that this resistive transducer as well as this is a passive transducer, and this works on the basis of familiar equations of resistance. We know that Rs rho L by A. Okay, so you can see here the strain gauge, how the strain gauge measurement is done by using a Wheatstone bridge. Okay, and we know the types of strain gauges are unbounded strain gauge and we have bounded strain gauge. So what is this unbounded strain gauge is here why we call it as an unbounded strain gauge. Strain gauge is not directly bonded to the surface, okay, which is subjected to stress or which is under study. Okay, so it consists of you know that it consists of resistance wire stretched between these frames. Okay, you could see here in this picture. Okay, these two frames are movable with respect to each other, and this arrangement will be connected in one of the arms of the Wheatstone bridge. So unbonded strain gauge are not directly bonded to the surface. Okay, and next these are bonded strain gauges. So bonded strain gauge are directly placed or bonded on the surface of the device or component, so which is subjected to stress. Okay, or which is under study. So here you have different types. In commonly we called as wire type strain gauge or foil type strain gauge, semiconductor strain gauges. Okay, so here you could see various types: linear, double linear, shear, rosette, okay, half bridge, full bridge. These are types of bonded strain gauges. So force measurement using strain gauge. Here the non-electric quantity, you know that displacement, force, pressure, temperature, which has to be measured, is applied in such a way that these will change either length or cross-sectional area of resistive wire. Okay, so resistive wire strain gauges, here it is known as piezoresistive gauge. So it is also used for the measurement of displacement, temperature and pressure. As this is a secondary transducer, it is also used for measurement of force and acceleration. Thus we know that. Okay. And next is force measurement using a strain gauge. So here you can see you know that quarter, half and full bridge configuration. So you know that first in quarter bridge configuration. So here a single strain gauge is used to measure the deformation caused by the applied force. Okay. So the strain gauge will be attached to the material or structure which experiencing the force. Okay. So As the force acts on this material, it causes a change in resistance in the strain gauge due to the strain. So by measuring this change in resistance, we will determine the force applied. Okay, this is quarter bridge configuration. And next, second one is half bridge configuration. So here two strain gauges are used to form a half bridge. Okay. So one strain gauge is placed on the top of the surface and other is on the bottom of the surface. You could see here an R1 and R4. So as the force is applied, strain gauges experience opposite changes in resistance. So the difference in resistance between two gauges is measured to calculate the force. Okay, this is in case of half bridge configuration. Then the third is full bridge configuration. In this full bridge setup, four strain gauges are arranged in a Wheatstone bridge configuration. Okay, two gauges are under tension and two under compression due to the applied force. So this is more sensitive and accurate as it compensates for temperature changes and provides a higher output signal. Okay, so by means of which you can able to measure the force applied. And next one is wrist force measurement using strain gauge. Okay, here the strain gauges are typically attached to specific locations on the wrist, as you could see here. Okay, so like brace or a wearable device, and are designed to measure the deformation or strain caused by the forces. Next, coming to the 6-axis force or torque measurement. Okay, here how this is named as 6-axis is, so 3-axis is force. Okay, along a 3-axis, that is x, y and z axis, force and torque together are measured. So along x-axis you could see here force, it is denoted as Fx, and the torque is denoted as Tx. Similarly, along the y-axis, force and torque, along the z-axis, force and torque is measured. Okay, so how will we calculate this force or torque measurement in 6-axis? Okay, this is generally represented as Maltese cross configuration. You could see here in this picture as this 6-axis force or torque sensors is kept between the wrist and the last link. You could see here. Okay, this is projected over here. So here you could see strain gauges is placed on the so you could see here it is strain gauges is placed in opposite sides. That is totally of 8 pairs of strain gauges are placed in this Maltese cross configuration, and we will be measuring the 6-axis force or torque measurement. So the force are named as Fx, Fy and Fz along all the 3 axes. And the torque, here the torque is measured as in moments. Okay, moments mx, my and mz. Okay, so about this we will see in detail. So these are the forces about the strain gauges are placed, right? So 8 strain gauges are placed. So it is 8 pairs. So each forces are measures are mentioned as W1 to W8. Okay, 8 pairs. So we'll see this how this has been calculated. Okay, you can see in this first picture as this where how the force 6-axis is placed. Okay, the Maltese cross configuration along x-axis, y-axis and z-axis. Okay, so as we have seen earlier, this in this x-axis, so you will have both force and torque. Here it is in moment. Okay, again along y it is Fy and My, that is force and torque, that is moment, and along z it is force and moments. Okay, And then the forces sensed at the spoke elements, that is the strain gauges. Okay, so that is I said, so you have 8 pairs, W1 to W8. So along all the first sensor coordinates, you can see here W1, W2, so W3, W4, W5, W6, W7, W8. These are the forces sensed at the spoke elements. Now, force syntax reference to XYZ sensor coordinates. How this will be calculated in this multi-cross configuration in matrix S. So we know that, okay, we know that you have 6 axes. 6 axes. So along 3 axes you have force as well as moments. Okay, so that is Fx, Fy, Fz is for force along all the 3 axes. Mx, My, Mz is moments along the 3 axes. Now you could see here the coordinate matrices as, so you have totally of 8 pairs, right? So you have totally 8 elements. So how this is named? Okay, now I am representing this as, so first take for Fx. Fx is along the force along the x-axis. In this, what are the moments? What are the forces? That is forces instead the spoke elements you could see. Okay, in this direction, what are the forces sensed at the spoke elements? Here you could see here K13 and 17, K13 and 17 are present. So in this subscript, the first represents the axis. That is 1 represents here axis. So 3 and 7 are the spoke elements. You could see here W3 and W7 are acting along the x-axis. Okay, so that is why 3 and 7 are named here. Okay. Next, coming to force Fy. In this, again, as it is in subscript, the first digit represents the which axis it is. Okay, so Fx stands for first, Fy is 2, Fz is 3, Mx is 4, My is 5, Mz is 6. Okay, so subscript always the first digit represents the which number the axes are. Okay, so here Fy, so it is numbered as 2. Okay, here 2 that is 1 and 5 are denoted. You can see here y-axis, Fy axis is along this. So in this direction, in this axis, what are the forces sensed at the spoke elements? You could see, you could see here in this W1 and W5. Okay, these are the forces sensed at the spoke elements. So that's why 2-1 and 2-5 are denoted. Similarly, Fz along z axis, what are the spoke elements sensed? You could see here. Okay, you could see here W4, okay, W2, W4, W6, W8. All the 4 forces sensed at the spoke elements are in the same direction along z-axis. So that's why you are named it as K32, 34, 36, 38. That is 2, 4, 6, 8 are the forces sensed at the spoke elements, and 3 represents which axis it is. So Fz stands for 3 here. Okay, that's why it is 3. Next, coming to the moments, Mx, My, Mz. Okay, so moments are the torques, right? So here you have to see Fx, the forces along the x-axis. Moments is, that is the torque in the same axis, right? So whatever you have seen as so along the force, you know that 3 and 7 are the Fx. Okay, along the forces along the x direction is forces sensed at the spoke elements are W3 and W7. Okay, what is opposite to it in the W3 and W7? What forces sensed what forces sensed at the spoke elements are opposite to this 3 and 7? You have to see, that is W4 and W8. So this will be the torque in the x-axis. Okay, so that is why it is named as 4 and 4-8. That is 4 and 8 are the forces sensed at the spoke elements. Okay, for strain gauges. Okay, and next My. So first you have to see the force along, that is Fy, you have to see force along the y-axis, you have to see. So that is W1 and W5. Already we have denoted that. Okay. So opposite to that, whatever you have it as the forces, since that opposite to 1 and 5 are W2 and W6. So this will be the moments at the y-axis. Okay. So that is why it is denoted as phi2 and phi6. And next Mz. Mz is, that is the moments along the z-axis. So first you have to check the force along the z-axis. Force along z-axis, you know that it is W2, 4, 6 and 8. So opposite to that will be your moments along the z-axis. So 2, 4, 6, 8. Opposite to that will be 1, 3, 7 and 5. Okay, 1, 3, 5 and 7. Okay. So 1, 3. So it is denoted as subscript as 6, 1, 6, 3, 6, 5, 6, 7. So 6 is common. 6 is your, it is denoting the which axis it is, 6th axis. And 1, 3, 5, 7 is your moments along the z-axis. Okay. And the last matrix W1 to W8. These are the forces sensed at the spoke elements. So this is how the coordinate matrices is calculated for this Maltese cross configuration. Okay. Typical specifications of this cross configuration, Maltese cross configuration is diameter is approximately 10 centimeter, height is approximately 5 centimeter, and it has a 50 to 500 Newton, resolution is 0.1 percentage, and 5 to 70 nanometer, so resolution is 0.05 percentage. Sample frequency is approximately 1 kilohertz. Okay. So two pair of strain gauges are mounted on opposite sides of each element, as I already told you. So totally 8 pairs you will have, 2 pairs opposite. Okay. So the two gauges of each pair are placed adjacent on the same beadstone bridge. Okay. So here requirement of force torque sensor. To make sure that the wrist motions caused by the force torque sensors don't mess up the accuracy of the robot arm, the sensors need to respond quickly to cancel out any interfering forces, allowing for precise readings in a short time frame. Okay, so the sensors should be compact and not get in the way of the robot's movements, ensuring it can operate smoothly. And they should be positioned near the robot's tool or hand to accurately capture the applied forces. So the relationship between the force or torque applied and the strain gauge readings should be straightforward and predictable. The sensor should be made from a single piece of metal to eliminate any hysteresis. Okay, so which can affect accuracy due to lag or memory in the system. And it's a measurement of external forces and torques, that is moments by 6-axis force or torque sensor. You can see here. It is taken from an article. And next, some of the applications for force control in manipulators are, you could see here in pictures, chamfering for bomb diffusing, surgery and prosthetics, grinding, deburring applications, assembly, product testing. So these force control are used. You could see in this pictures. Next, force torque sensor at work. You could see here the video.
Or on the factory floor. sensitive to noise than other force sensing technologies.
So this is about the force and the task sensors and robotics. Thank you.